Okay. All right. So hello, everyone. My name is Fernando. I'm a PhD student at NYU, and I have been working with solutions for reproducibility for quite a long time now. Actually, during my entire PhD, which is like a side project of my main thesis. And this, what I'm going to talk about today is my latest project, which is called ReproZip. So we have been working on this for 3 years now, all done by me. So now we have one of our main developers now is Remy. We also collaborate with the librarian for research data management and reproducibility, which is my advisor, and Dennis Shasha. So before I start, I just want to say that I don't have any background on neuroscience. Okay, so and I may present here a few examples using neuroscience. So if I say something wrong, just ignore. All right. So I don't think I need to convince you all that we do need reproducibility, but I like usually to mention a few of the reasons that I think are the most important reasons, right? So the first reason is to build on top of previous work. Of course, science is incremental. We never start something building on top of other people's work. And if you make a research reproducible, of course, it's easier for them to actually advance the science, right? Another reason, which was also related to that, is to help newcomers. So if you have a lab, and then you have new PhD students, new postdocs, new researchers, right? So if your research is reproducible, they can easily get to work. They can easily start using your stuff, so they can actually work better. One that's my favorite is to defeat self-deception, which is actually related also aligned to verifying the correctness of results. So we don't need to verify the correctness of results because we don't trust each other. That even anonymous people is a master of self-deception. So we're struggling with deadlines, and then we find actual results, and then we tend to accept those results because we are almost publishing something, right? But that's not how it should happen. So the fallacy in research right now is that we rigorously check the unexpected results. Expected results, we tend to give a free pass. Huge issue. So this is so there's this paper, should the Democrats move to the left on economic policy? So this was no, actually, way longer, 2008. They basically show that the Democratic candidates, they could get more votes if they moved more to the right and on economic policy. And then 3 years later, they tried to reproduce the results, and then they found out that there was an error in one of the variables of this study because they were using the wrong sign. Okay, so immediately one of the co-authors, which was Andrew, he published a correction and mentioned results sync perfectly reasonable, right? So they probably didn't try to look for other alternative hypotheses for such result, right? And one of the ideas to actually avoid this is just get a lab mate project and then give him hey, try to reproduce this. So kind of like being the devil's advocate, right? So that you can try to find other alternatives to your project and to see if you're actually following the right path. And of course, because reproducibility, because it's just good practice, or at least it should be. But although we do have many reasons why we should do reproducible research, you keep seeing on the news many things related to reproducibility, because many of these studies published in the past, they keep getting retracted because people cannot reproduce these results. And I mean, some of them are even dangerous. So there was even this cancer researcher that actually one of the people that were one of the persons that were the subject of the study actually died during the study, and then the results could not be reproduced, and then people were thinking, okay, maybe if it was reproduced, they could find the error before, and then this person couldn't have, died, basically. So, and actually some of the news are actually related to neuroscience. So there was this study last year, I don't know if you saw that, but basically they found out a bug on most of the softwares for fMRI, so there was a lot of lots of people comment on it. Some people said that it was not that a big deal. It's not as bad as it seemed. Some people said that we could actually give a rate of up to 70% of false positives in the analysis, and a bunch of papers in the past have used those software packages for the analysis, right? So I don't know if you...
The outcome paper did not find a bug. The outcome paper demonstrated...
There was a bug in one,
also
in Afni. Yeah, where we're very well familiar.
Yeah, see?
It's pretty much criticized our
Again, I don't
entire
have a
work.
background, so
Yeah, but it's not a, I mean, it, you know, the,
right, yeah.
But why is it just done on the statistical view? Anyway, it's been...
but I mean, it's relevant to what he's saying though, because if Anders hadn't done the study he did, we would have never
Yeah.
found those. So.
Yeah.
Yeah, I mean, I don't know if it's like as bad as it seems, but it's still like, it's shocking when you see some sort of news about like old papers, like old studies not being able to, be reproduced because of that, right? But of course, there are still a few obstacles to reproducibility, and here I'm just mentioning a few of them. So one of them is privacy confidentiality. I'm not sure if it happens in neuroscience, but in many other domain areas, I mean, you deal with private data, and you cannot share that, and sometimes it's even hard to anonymize the data. And not only about the data, but even the code. Sometimes you need to run on a software package that cannot be distributed for some reason, right? So then it gets really hard for people to actually try to reproduce your results. Also, cultural change, right? So we haven't been taught reproducibility since the beginning of our studies. This has been changed. So even at NYU, Vicky, who is a librarian, and now Professors Julian and Dennis, they best reproducible practice during their classes, right? So even using like GitHub, how you can actually improve the reproducibility of even your own assignments, right? Because it really starts since the beginning. But it's still, and there's a lot of people that still think that people could, steal the research. There's the issue of lack of attribution. Someone will use my code and won't even, give credits to me, those kind of things. And last, because computationally speaking, it can actually be really hard, okay? And one of the issues with reproducibility at computational level is related to, even if your research is runnable, your results may differ in different systems, or even on your own system after a long time. So this first study, maybe you also know the software ReproZip, maybe you're familiar with it, I'm not familiar. But they had this study in 2012 where they analyzed the effects of operating system libraries on this software, and how basically they tried to detect how these results changed. And they found out that there were differences found between different architectures, or even different versions of the same operating system. In this case, was for the Mac OS. And then 3 years later, there was another study which I think analyzed ReproZip and other two software packages, which I cannot remember the names. And then they found out that some of the results were different because there was a specific library that had different versions, and each version basically uses different precisions for the floating point numbers, right? So what the authors of the study they said was not really significant, but when you have large pipelines, right, this difference get accumulated, and then at the end, the results can be actually quite different. But the problem here in reproducibility is that people usually think of reproducibility having three main pillars, which are the paper, code, and data, which also includes the metadata. So if you have like those three things, you can basically reproduce the research. Even with those three pillars, the reproducibility can still fall into ruins because you still need a fourth pillar. And this fourth pillar is the environment, the computational environment. All the operating system libraries, everything that it's behind the computational also needs to be captured so that you can try to assure reproducibility in a long-term basis. So here, basically, we posit that the computational environment is as indispensable for reproducibility as the code, data, and paper. All right, so the solution, okay, we should capture computational environment. So we're done, right? The problem is that capturing environments is really hard. Okay, so we have a problem colloquially known as dependency hell, which is so you have like a library that depends on the library, that depends on the library, and so on. So you have this long chains of dependencies, and then perhaps if you have like a different version of one of those libraries, your results may differ. So, and it's really hard to detect those, and even if you detect those, then this other researcher that wants to reproduce your results needs to install all of those dependencies. And I mean, even I myself, I have tried like to install like a bunch of dependencies, and then sometimes they clash my own environment machine, but then one of the libraries is missing, and I don't know which libraries is missing. So it's a pain in the neck, right? So it's a very complicated problem. Well, of course, I'm not even here going into the subject of distributed systems, which is way more complicated than a single computer. And so here we have actually a gap of tools that can automatically capture all these dependencies for you, and at the same time, use that information to automatically set them up for you in another environment. So with that in mind, with that gap in mind, is that we came up with ReproZip, which we call the reproducibility packer. So in a nutshell, here how it works. So suppose you have your experiment, which may be a Python script, or something maybe more complicated that involves a server. So you have this on your machine, and then you use ReproZip to create a self-contained package of your research. So basically, it captures all the necessary files to reproduce your research. Self-contained package. So the extension that we use for this package, it's basically like a zip package, but we use RPZ. So whenever I say RPZ package, it's the ReproZip package. So you have this package. Now you're going to send to all your collaborators, your peers, or other researchers interested in your work, and they may be working on totally different systems. And then they can use ReproZip to unpack and reproduce the research. And here, when they create this ReproZip package, so currently, since we use a software package that is native to Linux only, so only do on Linux, but then for unpacking, we are able to do on Windows, Linux, macOS, because we can use virtualization environments for this phase. So basically, we have those two phases that we call packing and unpacking, okay? So I'll give now one more concrete example so that we can see how concretely ReproZip can actually pack and unpack experiments. So this example is basically, so I got it from, so I don't know how to say it, is it DiPi or DPi? I don't know, it's a software package for DMRI. I don't know if you say DiPi or DPi, I don't know. DiPi, okay.
Sometimes Eleftherius calls it Dippy.
It does?
Yeah, Eleftherius.
Oh, does he?
He sometimes calls it Dippy.
Dippy, okay. So maybe it's Dippy, okay.
Is the live stream started? I'm sorry.
Oh,
Yeah. Screenshot.
Did you do like start broadcasting?
Mm-hmm. Yeah. Didn't started it again. Can you ask them if they can see it now?
I mean, I can't see it.
Oh, you're looking?